Okay, let's get started. So we're going to start a new set of slides called the stellar graveyard. So I've introduced you to the lives of low mass stars, the lives of high mass stars, and now we're going to spend a couple lectures. So I'm going to split this set of slides between two lectures, kind of focusing on that very end stage of stars. Focus on what gets produced, what happens. There's these things called novae and supernovae that are some of the brightest events in the universe as stars can die, and they can produce these things called white dwarfs, neutron stars, black holes. Okay, so we're going to focus on the stellar graveyard. Remember, there's a quiz, as usual. There's a quiz this week available until Wednesday. Are there any questions before I get started? Okay, so as a bit of a reminder, right, we talked about kind of the mass range of stars. There's a lower mass range below which you get what are called brown dwarfs. So anything that starts out less than about 8% of the mass of the sun is basically a big, initially pretty hot Jupiter that we call a brown dwarf. It doesn't have fusion, it just kind of cools off. And it's just like a really big Jupiter-like failed star, something that never really entered the main sequence, right? It's never undergoing hydrogen fusion. Then we have low mass stars like our sun that go up to about 8 times the mass of our sun. And these, when they die, they end up producing what's called a planetary nebula. So when they die, they don't produce a supernova, but they do kind of, as they die, they create kind of a small explosion that blows out a lot of the material that they were made of, producing these beautiful nebulae. It's called a planetary nebula because a few hundred years ago, when people had not very good telescopes, they thought maybe there were planets in the process of forming because they just saw these blurry images. But so they don't have anything to do with planets. They're these just beautiful nebulas that in the future, though, could form solar systems, right? They're the stuff out of which new stars form. They're one type of nebula. And they leave behind this dead core of a star, mostly made of carbon. Some other stuff mixed in there, but mostly carbon, that we call a white dwarf. And white dwarfs are these tiny, bright objects. Well, they're not bright, but they're very hot, but they're not bright because they're so small, and they will cool off until the end of time. Okay? You get a more massive star up to about 20 solar masses. When they die, they produce this kind of extreme explosion, this cataclysmic explosion called a supernova. And as we'll talk about, then what's left behind is a neutron star, something more exotic than a white dwarf. It's literally like a giant ball of neutrons, like a giant nucleus of an atom, but really, with the mass of the sun. And then you can have hypernovae, which are just really, really big supernovae from really big stars that can be flying a black hole. Okay, so this is the arena that we're talking about today. I want to start with low mass stars. So first of all, remember this Hertzsprung-Russell diagram. This helps us situate both low and high mass stars in context. So remember, the higher mass stars are up here in the diagram. They burn bluer and brighter, whereas low mass stars burn more yellow or red, are less bright. Remember, brightness is y-axis, color or temperature is on the x-axis. And our sun is an example of a low mass star. It's kind of right in the middle. And as stars die, remember they move to the upper right. They get redder and bigger and brighter. And then when they finally die, they move down to leave these stellar remnants. And what you see here are white dwarfs. Okay, these are these tiny, so they're very small, pretty hot. They're towards the left of this diagram. They're hot, so they're kind of bluish, but they're so small they're not very luminous. They're hard to see. You see, they're about 100 times less bright as the sun. And here was this kind of cartoon helping you understand what happens to a star like the sun. So as it dies, as it begins to, so before it completely runs out of hydrogen, remember, it starts to build up this core of helium. That's what the hydrogen is fusing into. It's creating a core of helium. And because that core is inert, meaning it's like a solid ball that is, this forms like a wall against which the hydrogen pushes, it's supported by degeneracy pressure, meaning it doesn't expand and contract when it gets warmer or cooler, so it can't regulate the temperature of the star. Now, as a result, the star kind of expands and becomes a red giant. And at a certain point, actually, that core gets so hot that it begins to fuse the helium. So now you have a star that's fusing helium in addition to hydrogen, and it kind of moves back a little bit towards the main sequence because now it does have that regulatory power. The core is not an inert ball; it's now can expand and contract as it wants to cool off, or as the fusion rate goes up. Well, then it expands and cools off, and the fusion rate goes back down. So it has a regulatory mechanism. But then, what's helium fusing to? Well, remember the triple alpha process. It fuses mostly into carbon. So now you have an inert carbon core building up, and it becomes a red giant. So the last of the red giant stage, as again, it loses its thermal regulatory process, expands again. It's eventually, it reaches the point for a low mass star, it never can fuse carbon. So what happens is it eventually runs out of fuel, pushes out this planetary nebula, which is just mostly hydrogen, mostly what the star was originally made out of, hydrogen and helium and little bits of other elements, and leaves behind this dead core of carbon. The dead core is really hot because when the star dies, gravitational potential energy pushes down into on that core, but it can never get hot enough to fuse. So just as a hot, white hot, bluish white, but small, so it's not very bright. So it moves down here. It cools off over time, getting less bright and less blue. Okay, so that's the story of a low mass star. And this is an example of a planetary nebula. A lot of the beautiful pictures of nebulae that you see in astronomy photography look like this. Okay, lots of beautiful colors. I mean, you can see anytime you see something like this, where you have, first of all, you have darker regions that represent colder clouds of dust that is likely going to form stars because it's colder, so it can contract under gravity. But also lots of bright colors from stuff that's being heated up, nearby stars, emitting lots of colors. So what you're seeing is lots of gas and dust, either cold and causing kind of obscuring light, like you see here, or kind of warmed up and emitting light in various ways. And what you often see near the center of these planetary nebulae are white dwarfs, right? What's left behind after a star had died. So, as an overview, this is the exposed dead core. Normally, you don't see the core of a star, right? But where the fusion is happening is the very center. And what's left behind is, well, first of all, there's no fusion happening at all, but it's what was that core of carbon. No fusion, but it's just very hot and it's small. Most stars are lower mass stars. About 97% of stars are qualify as a low mass star, and in their lives as white dwarfs. So there's a lot of white dwarfs around. We'll talk about the Chandrasekhar limit. That's the maximum possible mass of a white dwarf, above which, so think of, so first of all, a white dwarf has about the mass of a sun compressed into the mass of the Earth. I mean, the size of the Earth. So it's like an Earth-sized thing that is the mass of the sun. So gravity is incredibly strong in a white dwarf. And what supports it from compressing into a black hole? Electron degeneracy pressure. It's just a bunch of carbon atoms that don't want to push into each other. But there's an upper mass limit, 1.4 solar mass, just the Chandrasekhar limit, above which gravity is so strong that the thing will collapse. And we'll talk about that. That produces a type of supernova when that happens. But otherwise, you have an isolated white dwarf. It'll cool off over time, okay? Eventually becoming a black dwarf, and you just don't see it anymore. It's just They're already hard to see because they're so small. But once they cool off, then they're not emitting enough light at all to see. So that's the overview. Let's go through just a few questions that I'll answer to help make sure you've covered the things that I need to cover. What is a white dwarf? It's the exposed core of a dead star, made of carbon mostly. What prevents it from collapsing under that incredible gravity? Electron degeneracy pressure. That's the fact that just atoms, the electrons surrounding atoms, don't want to overlap. That's the same reason why my hands aren't going through each other right. Okay. And here's a picture. So we see lots of them. Again, we have to look kind of nearby because they're not very bright. But if we look at a big cluster of stars, for example, in our galaxy, where lots of them have died, and remember, most stars are low mass stars. They produce, and we see lots of that. They're circled in this picture. And what happens if we look at them through a spectrometer? We see that they're mostly blue, so kind of whitish or bluish, so very high temperature. But as you can see, they're not bright, right? There's other stars nearby, these other stars that are kind of drowning them out. They're way brighter and they're yellow. Here's white dwarfs. What is the thing? What is the name of the pressure that prevents a white dwarf from collapsing, right? Gravity is really strong on a white dwarf. It's about the size of the Earth, but the mass of the sun. So huge amount of gravity on a white dwarf, but it's electron degeneracy pressure that prevents it from collapsing further. And let's look at a few examples. So here's and these are ones that we can study and have been known about for a long time because they're nearby. And perhaps most famous, Sirius. Sirius is the brightest star in the sky. It's Alpha Canis Majoris, so it's the brightest star in Canis Major. Here's Sirius, and it turns out it's a binary system. Remember, we talked about 50% of all stars, right? It might look like one star, but there's two stars orbiting each other, two or more stars orbiting each other, and Sirius happens to have a companion called Sirius B. You can see them both here. Here's Sirius A, invisible light, and it has a very dim little companion. So this was two stars, one of which has died already. That's Sirius B. It's left behind a white dwarf. But by the way, how are we sure, that this is a white dwarf? Well, one other thing you can do is look at it in a different wavelength of light. What if you look at it in X-rays? Well, here in X-rays, you see that it's really bright because while overall it's not a very bright object, Sirius B, it's very hot. It's small, so it's not emitting much light overall, right? But if you look into X-rays, Sirius A is emitting much X-rays, but Sirius B is so hot it's emitting lots of X-rays, so it's very clear. This is a very small, very hot object. Okay, it's a white dwarf. So this was one of the first examples of a binary star system discovered. It's close; it's only 8 light years away, and of course, it's a companion to the brightest star in the sky, Sirius A. So in 1844, Frederick Bessel, someone that may be a familiar name if you take a lot of science classes, discovered that Sirius is a binary star. Here's kind of what their orbits around each other look like. Here's the redder Sirius A, and then the kind of bluer Sirius B. And so Sirius A is Alpha Canis Majoris, but because that thing that to the eye looks like one object was called the brightest star in Canis Major, Alpha Canis Majoris, but later this object was discovered to actually be 2 stars. Okay, what we typically think the main bright star in Sirius is called Alpha Canis Majoris A, and the little white dwarf is given the name Alpha Canis Majoris B. And so that's how we name, even though it's actually 2 stars, both called Alpha Canis Majoris, we now label the bright one A, the white dwarf B. And here are the characteristics you see when you study it. The Canis Majoris A is about 10,000 degrees, so it's bluer than our own sun. But the white dwarf is really, really hot. That's why you can see it in X-rays. It's 27 degrees Kelvin, 27,000 degrees Kelvin. What you get from studying these orbits is that Canis Majoris A is about 2 times the mass of our sun. So it's also a low mass star, whereas this white dwarf is about 1 solar mass. That's typical. The luminosity of Canis Majoris A is about 23 times the luminosity of our sun, but this white dwarf is only overall about 3% as luminous as the sun. So this is typical. It's about a whole sun's mass, but compressed down to the size of Earth, so it's not very luminous, but it's very hot. Here's another example. Instead of Canis Major, if we go to the constellation Canis Minor, the brightest star, Alpha Canis Minoris, we also call Procyon. Here's a nice picture where, again, if you look close, right? So initially you just called this whole system Procyon, but now we call the brightest one A, and you see this little fainter bluish one, B, Procyon B. Okay, Procyon A is about 1.5 times the mass as the sun. Procyon B is about 60% the mass of the sun, and that's a white. Now, these white dwarfs are made mostly of carbon. So this is because, remember, again, hydrogen first fusing to helium, then helium through the triple alpha process fuses to carbon. In higher mass stars, you start to have these helium capture processes where like carbon captures the helium to become oxygen, and so on up to silicon, up to iron.
Huh.
That some of these white dwarfs have crystallized. So literally,
What the heck?
they're crystals. There's the first discovery in 2004 of a white dwarf. At the time, known to be the largest gas by a kind of solid. That's kind of cool. Here's just a picture of kind of the size of a white dwarf compared to the Earth. So one interesting thing about white dwarfs, now we saw an example of this before with Jupiter. You add mass to a white dwarf, it actually gets smaller, right? Normally you think if you add mass to something, it should get bigger. But in the case of a white dwarf, we saw this also with Jupiter, that mass, it actually will start to get smaller because gravity is, as you add more mass, gravity gets stronger, it pulls in harder and harder. So it actually starts to shrink as you add. Here's a 1.3 mass white dwarf. Remember, the limit is 1.4 solar mass. So we'll talk about that in a second, because what happens is it starts to shrink until, gravity gets so strong, it can't prevent itself from collapsing. So gravity is so strong in a white dwarf, just because it's so dense, right? All that mass, the mass of the entire sun, all compressed down to the size of the Earth, smaller. So if you were to just take like a teaspoon of a white dwarf, it'd be like a ton. That's how dense it is. So like just as an overview, make sure you're familiar with some of these basics. Quizzes, which of the following is closest in size to a white dwarf? You're gonna have to remember this because it'll be different from like say a neutron star. In the case of a white dwarf, it's about the size of the Earth. It's a good handy way of remembering how big a white dwarf is. About the size of the Earth. And if you took just a teaspoon of material from a white dwarf, it would weigh a few tons. That's just how dense stuff is. All that mass compressed into small size. Okay, and again, important to remember, even though it's so small, how big is a white dwarf in mass? It's about the mass of the sun. All compressed down to the size of it. Now, as you add mass to a white dwarf, as I said, it gets smaller. Gravity just keeps getting stronger and stronger. It gets denser and denser. It turns out that there's a limit you can calculate, which is the point at which gravity wins. Okay, and this is the white dwarf limit, or the Chandrasekhar limit. Now, the idea is that the electrons that are pushing against each other to prevent from falling into each other and press stuff together, they have to move faster and faster in order to prevent collapse. And what Chandrasekhar calculated was that the electrons in a white dwarf start to approach the speed of light. Now, that's the absolute speed limit in the universe. Nothing can go faster than the speed of light. So as electrons are trying to stop this white dwarf from collapsing, that's to produce that pressure called electron degeneracy pressure. The electrons have to start to go to the speed of light, which is impossible. So at that limit, about 1.4 solar masses, a white dwarf will collapse. Okay, and so here's a nice picture kind of illustrating Chandrasekhar's calculation. If it weren't for relativity, as you make the mass of a white dwarf larger to the right here, it'll just keep getting smaller and smaller. So if you imagine this blue line, 1 solar mass, 1.5 solar mass, it just gets smaller and smaller and smaller. But if you include relativity, what you find is the green line. And it gets smaller, but at a certain point, near about 1.4 solar masses, its radius will just shrink to 0 because those electrons won't be able to push back fast enough to keep this object from collapsing. And so before we talk about what happens when that case occurs, why is there an upper limit to the mass of a white dwarf? Well, I put it as the more mass of a white dwarf, the greater the degeneracy pressure, right? That's what's keeping it from collapsing. So the greater the mass, gravity is stronger, you have stronger degeneracy pressure, atoms fight to keep from pushing into each other. But those electrons have to move faster and faster. Near about 1.4 solar masses, the speeds of the electrons are going to the speed of light, and you can't support any more mass. The object will collapse. So that the exact mass limit that you have to remember is 1.4 solar mass. Upper limit. You'll never see a white dwarf above 1.4 solar mass, which is something we can test. Look out with the telescopes and see. Never seen a white dwarf above 1.4 solar mass. Okay, and then another thing I want you to remember, if you do have a white dwarf that just is not collapsing, it's just sitting out there, it doesn't have something to add mass to it, so it's just isolated. What's its ultimate fate? Well, it'll cool down over time, eventually become what you might call a black hole. It's no longer white, it's cool, cooled off. So you just don't even see. Any questions before we move on to talk about what happens if a white dwarf collapses? Exotic phenomena. Okay, so now we get to some of these energetic events in the universe called novae, white dwarf supernovae, and then we'll even talk about other types of supernovae. But for now, we'll cover something called novae, which is different from a supernova. And a special type of supernova called the white dwarf supernova. So one thing that can happen is you don't have an isolated white dwarf. So here's an artist's rendition of you have a white dwarf here, and then you have its companion star. So remember, about 50% of stars have companion stars that orbit each other, and one is going to die first. So you have, say, a low mass star that dies, produces a white dwarf, that's shown here. And its companion star, especially when that companion star enters this red giant force, it starts to expand, right? And this little white dwarf starts to eat up some of its outer atmospheres, right? So here's an example of an accretion disk forming around a white dwarf, because it's kind of feeding off material from its nearby Well, what's going to happen? Well, mass is being added to this white dwarf. Right? So a number of things happen. First of all, you just see here in this artist illustration, it's called the accretion disk. That is, you have mass. You have mass falling towards this white dwarf. Okay. And so it orbits. So it's orbiting the white dwarf. But what happens is there's friction between these other particles in this accretion disk that allows some of the material to fall in. Okay. That also causes the accretion disk to kind of heat up and glow. So we typically see them. In fact, they make it hard to sometimes see the central white dwarf because the accretion disk is so bright. But what can happen is that this white dwarf is made out of carbon, but the material from the star is mostly hydrogen. So you're getting a layer of hydrogen falling down, getting really hot, compressed onto the surface of this hard, hot carbon core of the white dwarf. And it's going to get hot enough to cause fusion of all that hydrogen to form a layer around this white dwarf. Okay? And when that fusion happens, it's like a bomb bomb. It's a very sudden, violent explosion because that fusion kind of all happens at once. And typically, because gravity is so strong, kind of prevents this thing from entering a phase where it kind of regulates the temperature. No, the temperature goes sky high, and it all happens. All that hydrogen gets fused at once. This is called a nova. It's not as bright as a supernova, but it's incredibly bright. And these cause so nova refers to a new star. The word refers to because if you have a nova, you look up in the sky, suddenly there's something that's so bright that you didn't see it before, but now it looks like there's a star in the sky. And then it'll eventually go away. But this is
What?
But it also produces a nebula. So here's an example of a nova. Still see the white dwarf. This doesn't destroy the white dwarf. The white dwarf stays around. It actually multiple more matter.
What? You go to class at 12 something, no? Go away.
Right out front of it. And it leads to three. Expanding field of three. You see nova when you have binary companions. Gaining material from the outer layers of the star, that material falls down under the white dwarf, and suddenly it explodes. Because that material was hydrogen, suddenly fused into helium. Here's some true false statements about nova. It's true that a star that undergoes nova can undergo another nova. The white dwarf. If it's just a nova, because material accumulated on its surface flew off. It fused stuff on its surface to create enormous explosion. That central white dwarf is still alive. That central white dwarf. A nova, yes. Nova involves our sun. Will our sun undergo nova? Well, our sun doesn't seem to have a binary companion. Right? So it's false that our sun will undergo a nova. Our sun will become a white dwarf. If we don't have a nova, we don't have a companion for the sun to gain material that would fall down on the sun. It's periodic. That's false. Let's see, this is true. When a star system undergoes a nova, it brightens considerably. Okay? But not as bright as what we will talk about, supernova, the more catastrophic. And the word nova does mean star. It originally referred to a star that suddenly appeared in the sky. It appeared after a few months. So that's also something to remember about how long these events happen in terms of being able to see something in the sky that didn't even appear before. That's how bright it is. type of supernova that involves a white dwarf as well. That's something that you can imagine might happen if you have, again, just like we're talking about the nova, you have material falling down onto a white dwarf. Now, remember, a white dwarf has an upper mass of 1.4 solar masses. So if you do have a binary companion and matter from that accretion disk is falling down onto the white dwarf, that white dwarf can suddenly get over that mass limit. And then something catastrophic. It's called a type 1A supernova. There's different types of supernovas we'll cover in this course. Type 1A is so explosively violent, it literally is 4 billion times as bright as our sun. 4 billion times brighter than our sun. That means it's as bright as a whole galaxy. And so remember, a white dwarf is a burned out star that is supported by electron degeneracy pressure. Very dense, mass is about the same as the sun, and it's the size about of the Earth. It's about 200,000 times as dense as the Earth. And remember that white dwarfs become unstable when their mass reaches the Chandrasekhar limit of 1.4 solar masses. And a white dwarf, remember, is made out of carbon. So what happens if this white dwarf can no longer support itself as it overcame that Chandrasekhar limit, it starts to collapse. So now these carbon atoms start to overlap. They're pushed into each other. And what happens is it immediately fuses carbon with carbon form. And essentially this entire carbon star about the mass of the sun, all those fuses everything. So this is something that destroys the white dwarfs. Here's an example. These things are so bright that as bright or outshine entire galaxies. Normally, you don't see individual stars. There's another galaxy. All the individual stars, billions of stars added together, produce this kind of no glow, like the same glow points away. You don't see individual stars. But here is a supernova, type 1A supernova. So bright that suddenly there's this super bright star that's as bright as the entire galaxy. Otherwise, supernova remnants. So here's a case. This was a supernova that went off about 1,000 years ago. This type 1A supernova, violent, catastrophic explosion leaves behind this expanding bubble of hot plasma. And so here's an example, right, of applying what we've learned about the Chandrasekhar limit. So that's 1.4 solar masses. If you have a white dwarf, say it's close to that limit, 1.4 solar masses, right? And suppose it has some companion, so some material is grabbing that companion, settles down on this white dwarf surface, and its mass is now too high. It's higher than the limit, so it starts to collapse. What happens? Well, this white dwarf, made of carbon mostly, suddenly starts to collapse and it detonates. All that carbon fuses, creating the supernova explosion. Tremendous amount of energy. It's very, very good. So here, this was our same overview slide that I showed in part before. And what did we learn about white dwarfs? In addition to the basic facts here, most the end of life of most stars are the white dwarfs. But what can they do? There's a primary companion. Multiple novae. So nova, multiple novae, that is hydrogen in a shell around the carbon core suddenly fuses. Might happen multiple times. Or the whole thing, its mass, enough stuff settles onto the white dwarf, its mass goes above the Chandrasekhar limit. The whole thing, all that carbon suddenly fuses. So we have kind of three inputs that cooling off white dwarf, black dwarf. You have a white dwarf that something like novae, and you can have a white dwarf that's totally obliterated. That can happen. The novae and supernovae can happen. Close binary system. Matter from its close binary companion can fall into the white dwarf. That can lead to a nova or a white dwarf. Any questions about white dwarf, novae, and supernovae? So, there's another type of supernova. So let's talk about, first of all, let's remind a little bit about what we just covered. So the whole topic of novae and supernovae includes what we just talked about, white dwarfs. White dwarf, just novae, is that nuclear explosion on the surface of a white dwarf of accumulated hydrogen. Whereas heated to the point of centimeter cubes. That leaves the white dwarf intact. There are multiple novae in the future. I actually didn't say before, it produces a luminosity for a few weeks, months, or about 100,000 times the sun. So novae are very, very bright. But it's not as bright as supernova, which is when the entire white dwarf, talk about different types of supernova. Talk about the white dwarf, type 1A supernova, which is when that whole white dwarf suddenly, all that carbon suddenly on the most. In general, there's other types of supernovae we're going to talk about. In general, supernovae are about 10 billion times as bright as the sun. So long. They can outshine an entire galaxy. Okay? We talked about white dwarf supernova, type 1A. That's carbon fusion suddenly so white dwarf in these binary systems. Which is the Shadowseiko limit. The whole thing explodes. Nothing is left behind except for this beautiful nebula. But there's other types of supernovae called type 2. And this is doesn't have to do with white dwarfs, it has to do with more massive stars. Remember, white dwarfs are only what happens to low mass stars at the end of the But we're talking about also high mass stars, which actually have a lot more mass. These also very, very violent end-of-life scenarios. In particular, high mass stars have iron cores. Okay, remember, because they can fuse carbon, they can fuse, there's hydrogen, the helium, and carbon, right? Oxygen, neon, silicon, and so on, up to iron. Well, what iron core of a giant star that may be much more massive than a white dwarf. Reach this limit as the star dies, that iron core begins to collapse because it has so much gravity, it can't support itself against electron degeneracy pressure. Its electron degeneracy pressure is not strong enough to support itself, so it collapses into a neutron star. So now it's collapsing. This iron ball collapses. It can't support itself. It collapses into a giant nucleus called a neutron star. Or, in the most extreme case, it might collapse to a black hole. Even a neutron star couldn't. The mass is so large that even a neutron star would prevent itself from collapsing. Okay, so this is a type 2 supernova that occurs when this happens. And similarly bright as a type 1 supernova. As a reminder, for high mass stars, right, they don't have spores of carbon. They start eventually accumulating core of iron because that's the point at which you can't fuse iron. You fuse hydrogen and helium, the carbon, start fusing heavier and heavier elements until you eventually reach iron. That's the word we showed, the curve of binding energy. Iron is the point where you have heavy elements that decaying fission, they end at iron. When the fused elements also end at iron. Iron is the end by their fission or fusion. So the core of a high mass star ends up having iron, and then you can't fuse anything. Eventually you run out of energy from being able to fuse anything up to iron. And you have this giant ball of iron. It's incredibly dense, incredibly massive, and gravity is very, very strong. And at that point, this iron is so large, gravity is so strong that electron degeneracy, that's just preventing those iron atoms from pushing into each other. It's not strong enough. You can't prevent those iron atoms from pushing into each other. And the way those atoms push into each other, something has to give. And what happens is the electrons get pushed into the nucleus. So the electrons combine with protons. Electrons are negatively charged, protons are positively charged. What happens? Electrons combine with protons to produce neutrons, and then we talk about this nuclear process that also produces neutrinos. So we end up combining electrons and protons, producing a huge number of neutrons and neutrinos. Or collapses. The object is like a giant core of an atom. That giant, incredibly dense, and an incredible amount of energy. For all that gravity that suddenly collapses, it's violent, and this amount of energy. Type 2. Generally, similar brightnesses between type 1 and type 2. We can tell the difference. So here's some example of light flares. Suddenly you see a star go bright in the sky, and then over the course of weeks or months, in this case, so going from like 0 to like 70 or 80 days, you see the star get brighter and brighter and brighter, reaches some peak brightness, and then it just gets less and less brighter. What we see is that type 1A supernova tend to last a little bit shorter and reach a peak brightness that's a little bit brighter compared to these type 2, which last a little bit longer. So type 2, say, in the blue curve, doesn't reach quite as bright, but less. We can tell them apart. We can tell one is made of white dwarf, carbon material, and another still has some hydrogen around. Because, for example, when you look at the spectra, look at a type 1 supernova and the white dwarf, it doesn't have hydrogen. See that? It's all carbon. Whereas one of these supermassive stars still has some hydrogen, still has some helium, still has some other things other than carbon. So now we've covered 3 out of these 4 examples. Some from a brown dwarf, that is, the star never reaches the point where it can use hydrogen, less than 8% of the mass of the sun. We talked about low mass stars, the big white dwarfs. And the white dwarfs, if they have a binary contagion, can still have some fun. A white dwarf is a nova, or the whole thing can be obliterated in type 1 supernova. And rarer are high mass stars. High mass stars, when they die, produce either neutron star or black hole. I've just talked about neutron stars. That's if you have a star that's up to about 20 solar masses. When it dies, that iron core collapses. But the endpoint is a neutron star. Leaves behind, we'll talk more about neutron stars. It leaves behind this tiny, ultra-dense neutron star. But it itself doesn't collapse because after electron degeneracy pressure, there's something called nuclear degeneracy. Neutron degeneracy pressure. Preventing the neutrons from wanting to push in. But even that has a limit. So for stars more than about 20 solar masses, even a neutron star cannot support itself against a collapse. So at that point, we know no more physics that can and particles overlap. So as far as we know, what gets produced in a black hole, all the matter just squishes down to nothing. So that's another object to talk about. If you just give them those, that happens, they're even more energetic than activities. Call them a height. That covers the whole spectrum of life of stars. If we look to this example, this is a nice example of something I took a picture of a very
class. You go at 12:30. Get out.
Astronomers had noted new star, but they didn't call it a supernova. They just saw that there was a star in the sky. And we now know this is the Crab Nebula. So 1,000 years later, it's this beautiful nebula. It's expanding cloud of gas and dust. But it's a type 2 supernova, and it leaves behind the neutron star. I'll talk about. By the way, I might as well show you time lapse now. Of course, we don't have pictures, unfortunately, going back 1,000 years, but we do at least kind of watch a little bit as over years still expansion of this nebula. But it's still relatively young, 1,000 years. It's still expanding at violence. But anyways, there's lots of beautiful examples of these nebulas that are not planetary nebulas. They're produced from supernova, type 2 supernova. There's a 400,000 or 40,000 supernova. And as we'll talk about, very center of this neutron star. In any case, you see it's very beautiful. It's just kind of a giant bubble of hot gas. Okay, so what I want to talk about now, for the remainder of the neutron stars. Are there any questions about supernovae? Or talk a little bit about this really exotic object? So, first of all, after one of these supernovas from a really massive star, it's the end of life of any really massive star. What's left behind? Well, it's either going to be a neutron star or a black hole. So we're going to spend some time talking about both of these options. Right now, we're going to talk about a neutron star. Now, a neutron star is an incredibly dense molecule. Now, if you think of an atom, most of an atom is in space, and most of the mass of an atom is tiny, it's about 100,000 inside the atom. So a nucleus is incredibly dense. A neutron star is like a giant, it's just made of neutrons. So gravity is incredibly strong, it's so dense. What prevents it from collapsing? Well, neutron determinism. It's the same as electron determinism. It's just now you have neutrons that don't want to overlap. So again, as an effect of quantum mechanics, particles like neutrons don't like to overlap. And this state of giant ball of neutrons forms because you had this giant core of iron of a dying star that no longer was fusing, so it just had to collapse. Neutron star. And one of the ways we can detect neutron stars is because sometimes they pulsate. It's called a pulsar, which stands for pulsating star. Now, remember, if we have an ice skater pulls his arms in, due to conservation of angular momentum, you spin up, right? If I had my roller chair, I would do it. It's fun. You roll around, then you pull your arms in, you spin faster and faster. Now, a neutron star is so compact, so much mass has been pressed down to such a small size, it can be spinning very, very rapidly. And also, because it started out with a magnetic field, this pulsar, as it compresses, also has a very strong magnetic. As we talked about, this rapidly spinning object can therefore emit electromagnetic radiation. It emits like a searchlight, a beam of light that sweeps across the sky and allows us to see it, to see something in the sky that pulses at a very precise time. We'll talk about that in a second. It's called a pulsar, a characteristic signature of a neutron star. Another thing we can see is like the same, right? So we talked about white dwarf novae. The exact same thing can happen, but on a neutron star. So if you have a binary system, one of the stars died, but it was a massive star. Instead of leaving behind a white dwarf, it's behind a neutron star. And that neutron star can gather an accretion disk material can fall on a neutron star, and then suddenly that material can fuse right back, mostly hydrogen. Suddenly fuses, producing, well, we don't call it a nova, we call it an X-ray version. Because generally gravity is so much stronger that it's compressed at such a hotter temperature that it all happens much more quickly. It's like hotter, intense flash of X-ray. So those are two kind of characteristic signatures of neutron stars. Now they were proposed in the 1930s, just after we developed kind of, this was a time just after the invention of quantum mechanics, just around the same time that people proposed that there was such a thing as a nucleus and an atom, that there was fusion, the power of the sun. People proposed at that same time that there could be these stars that are just made like a giant nucleus. So people proposed the concept of a neutron star in the 1930s. And the first discovery of a neutron star was discovered through pulsars, okay? Through radio waves. Jocelyn Bell and Anson Hewish discovered in 1967. I'll talk more about that in a second. They're supported against gravity by neutron genetics and partial gravity, as we'll talk about, is incredibly strong on the surface of a neutron star. And remember, we talked about the Chandrasekhar limit. That's the mass above which a white dwarf will collapse. Well, there's a similar limit for a neutron star, the mass above which the neutron star will collapse, this time to a black hole. That's called the Tolman-Oppenheimer-Volkoff limit, DOV limit. Oppenheimer, you may have heard of, is the head of the Manhattan Project in the US, an atomic bomb. So it's called the Tolman-Oppenheimer-Volkoff upper mass limit. It's 3.2 solar masses. So if you ever get a neutron star that gets above 3.2 times the mass of our sun, it can't support itself against gravity, and it collapses. As a result, neutron stars can range in mass between 1.4 solar masses. Below that, it would be a white dwarf. So it's 1.4 solar masses up to 0.2 solar mass. That's what we see. And so even though they're more mass than a white dwarf, which is already a tremendous amount of mass compressed to the size of the Earth, a neutron star has a tremendous amount of mass, more than the mass of the sun, pressed down to the size of a small city, about 12 kilometers inside. So that's so dense. A teaspoon of a neutron star would weigh more than Mount Everest if brought to. Neutron stars are incredibly dense. There's a supernova remnant, Cassiopeia A, containing a neutron star. It's very important. There's neutron X-rays. Illustration. Now, there's some interesting things we can talk about with regard to something that's so dense, gravity is so strong. Okay. What you're looking at is, if you could, print a checkerboard pattern on the surface of a neutron star, look at it, what you would see, I don't know if you notice what's weird about the picture, but you can see both the North and South Pole at once. Okay, that's because gravity is so strong that a neutron close to a black hole, where light couldn't even escape, like, get it back down. In this case, what's happening is the light from the neutron star is trying to escape about out the opposite side. So, like, light from here would normally travel behind the neutron star, but gravity is so strong that it's pulling the light, okay, around toward the eye. As a result, you can actually see that here is about what we normally see, right? We just barely see the edge of the North Pole, edge of the South Pole. Here we're seeing around the to the behind. Here it's behind, behind, behind. Seeing lots of the other side of the neutron star. Light is actually literally bending around. This is typical of the neutron stars. That incredibly dense gravity, just incredibly strong. It begins to be exotic example. So one example of just how dense it is, so that just even took even less than a teaspoon paper clip of a neutron star, brought it to the Earth. It's so dense that it would be like Mount Everest. Imagine trying to pick up that paper clip. Okay? That's because a neutron star is like a sun, more than the sun's mass, pressed down to the sun's. Right, so which of these options is closest in size to a neutron star? About a city. City is about the size. And so this is the sort of thing to keep in mind, like for quizzes, right? A white dwarf is about the size of the Earth, but the mass of the sun. Neutron star is even more massive, maybe twice the mass of the sun, or even smaller than the mass outside. Now, how were pulsars discovered? Right, remember, this is one of the ways you can tell a neutron star is a neutron star. Well, in 1967, Jocelyn Bell noticed regular pulses of radio waves coming from a single part of the sky. This was really weird at it. Right? People thought, could this be aliens? Seriously, because if you point a telescope at the sky, you don't expect something so regular like a clock, right? What could cause that? Okay, as we'll talk about, it turns out the explainable neutron star. So here's like what you saw, like a pulse of light every second or two. Bump, 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 bump. And if you look at those peaks really carefully, they're actually precisely 1.701 seconds apart. They're incredibly precise, like a clock, like a really good clock, better than most clocks on Earth. Way better than the clock. Right? Very, very precise, repeating pattern of peaks. There's Jocelyn Bell. It's just kind of a cool example of the fact that, hey, in physics, a lot of famous names made their big discoveries when they were students. Right? So she was a 24-year-old graduate student, made one of the greatest astronomical discoveries in the last 100 years. But she was just analyzing miles of thing, miles, that was literally like little squiggles on a piece of paper, miles long. Looking at this by hand, she noticed this regular pulse. And this is something you see over and over again in the sciences where now you're tempted, partly because you're just lazy, right? You don't want to, I'm seeing this weird thing, I don't want to go into the Huffles and ask people about it. You don't want to be seen as making a big deal out of nothing. You don't want to, you're worried that, people probably already know about this. No, she did the right thing as a good scientist. Tried to figure out what was going on, what is causing these little regular pulses. And they eventually discovered that this originated from a specific object. You wonder, like, wait, pulsar. Discovered. Of course, now we have hundreds of pulsars. And the idea, the way it works, and it stands for pulsating star. You have this very tiny, incredibly massive star. Initially, stars have a strong magnetic field like our sun, like all about the magnetic field of our sun. And when all that gets compressed down to the size of the stick, magnetic field gets compressed too. It's really strong. And the star itself is spinning very, very fast, right? Concentration of momentum. And is that the neutron stars has some axis of rotation. So that axis is pointing up, spinning like this. Well, where the north and south pole of the magnetic star doesn't necessarily line up with the axis of rotation, just like on our own Earth. On our own Earth, the north and south pole, described from the rotational axis there, does not line up with the magnetic south pole, right? The north and south pole, right? Your compasses don't point exactly towards the true north and south pole, but just the magnetic north and south pole are not the same. And it's the same with neutron stars. They can have a magnetic field that points in a different direction, so the magnetic north and south is swept around like this, like a searchlight. As the star rotates at a very precise rate. This massive object that rotates exactly the same every time, over and over and over. So the searchlight sweeps across the sky at exactly the same pace, like once a second. And what happens is this magnetic field corrals charged particles along its axis that emit radio radiation. So you see this kind of sweeping of radio waves across the sky. At very precise levels. And that Crab Nebula, which was a case where it exploded 1,000 years ago, is one example. If you look closely at the center of this, it's hard to see visible light, but if you say look at radio waves, you get a pulsation every 30 times a second. There's another view of the Crab Nebula where look in X-rays, actually see the center where it's really hot, see the neutron stars like range. So you can actually see the poles when it's kind of shooting out a jet of stuff. Here's another example of a movie where you can actually kind of watch as this thing's kind of spitting stuff out along its axis. See, this is the axis about north-south of this, spinning like this. It's glowing like an X-ray. X-ray, very hot. You see this stuff going up like an axis. Large particles fall. Actually, nowadays these pulsars, neutron stars, are studied really well. And we know they must be neutron stars because they spin rate. Spin rate is so fast, okay? They can go up to like 1,000 times a second. But if you work out, because the size of a pulsar, it's about, say, 60 kilometers around. Well, something 60 kilometers around, and it's going 1,000 times a second. They actually, it's approaching the speed of light on the surface. So these neutron stars are incredible objects. What I'm getting at though is that it's spinning that fast. Sort of kind of centrifugal effect, right? This wants to rip this object apart. Right? It turns out the only thing that we can think of in physics that could possibly rotate that fast without being ripped apart is neutrons. Right? It cannot be some normal a giant block of steel. Anything like that would be ripped apart. The only thing that could possibly explain something that would rotate that fast but not ripped apart is a neutron star. Okay, so here, let me give you a couple opportunities for some poll questions.
What is a pulsar?
What is a pulsar? What is a pulsar?
Pulsar. What is a pulsar?
more second. Okay, and the majority got rapidly rotating star. Let's see, the next most common answer was a neutron star or a black hole that happens to be in a binary system. So maybe people said this because we were talking about binary systems. That's what can give rise to, for example, nova or an X-ray burst. But a pulsar, it's kind of how we discovered neutron stars, and one of the main ways of studying is because they're rapidly rotating, these pulses of light, which gives them pulses. Let me give you one more. Give you one whole question. Right, how do we know that pulsars must be neutron stars? So we just talked about, which is a strong piece of evidence for why pulsars must be neutron stars. 10 more seconds. All right, so again, most people got the correct answer. No massive object other than a neutron star could possibly spin as fast as we observe pulsars to spin and not blow itself apart. The second most common answer is that pulsars have the same upper mass limit as neutron stars. Now that's true. So you never see a pulsar more than about 1.4 solar masses. It's a little bit of evidence. Yeah, that's part of the evidence. But it's definitely not the strongest piece of evidence. All right. Stop sharing. Okay, and I think this is a good place to end. We're going to finish this lecture on Wednesday. Are there any questions before that? So I'm going to ask the second poll question. That is not again good answer. No. Yeah. So how do we know that pulsars must be neutron stars? So we definitely don't know that they must be neutron stars because of D. They have the same mass limit neutron stars do. That's pretty weak evidence. That's good though. That's consistent with what we expect, right? You wouldn't expect a pulsar to be way bigger or smaller than expected mass. But the real point that I emphasized, the really clear reason why we know that pulsars must be neutron stars is that nothing could possibly spin as fast. Still solid. All right. We'll see you Wednesday. Have a good couple days.